All right, welcome back to Mr. P Helps with Calculus. This is Unit 1, Day 5.5. We're going to be talking about the squeeze theorem, and we're going to be using that squeeze theorem in order to find limits of some trig functions. So let's get right started into it. So what is the squeeze theorem? And some people call this the sandwich theorem. So what it states is basically is that if you have one function that is always in between two other functions, it means it's, one function is always above it, one function is always below it, then no matter what, if they happen to be squeezed down or sandwiched down to a singular point, then the one in the middle would have to be the same as the two on the outside. So in other words, they would have to have, so basically if f of x and h of x have the same limits, meaning they have the exact same height at the same point, so if g of x is in between these two and these two happen to be the same, then obviously g of x has to have the exact same limit. So because that just makes sense because it got squeezed down to a singular point. Now when you see the picture of an example, it's going to make a lot more sense. So we have the black x squared, the red is negative x squared, and then the blue function happens to be sine of 1 over x squared. Now, what's important about this, and the reason why this meets the sandwich theorem, is because the blue function is always, no matter what x value you choose, it is always in between the heights of the red and the black function. So it's being squeezed down into a singular point. The closer you get to 0, the closer the blue function gets to meeting the same height as the black and red. So basically, since black and red have the exact same height at 0, 0 squared and negative 0 squared are both 0, it's squeezing or sandwiching down the blue function. And you can solve this algebraically, but yes, if they both happen to be the same limit, the black and reds have the same limit, then obviously the blue would have to also be the same because it can't be in between two things that are the same. It has to be the same as those two things. That is just the natural progression. Now, there's all sorts of videos out there that you can watch that shows this algebraic expression, but I really love this example. I just don't have enough time in my video to meet everything that I want to do. But basically, if I'm going to break this down a little bit for you, so what you have is you have three different triangles. And you have a triangle that's inside the circle, a triangle that's actually a sector. It's actually part of the circle. So it's a triangle with this little added bonus, which has got to be a little bit bigger. And then you've got this triangle, obviously, which is going outside the circle. And if these angles are all the same angle, then therefore this would have to be the biggest triangle. So this would have to be in between, because it's literally this triangle with a little added bonus. And then what you can do is you can solve it down and see that they have to all equal 1. So we don't know what theta is. Theta could actually be anything, but it's squeezed down to 1. So the smaller that you're going to make theta, the closer and closer it's going to get to 1. And algebraically, you can solve it right here. Like I said, just use the formula for a triangle, base times height divided by 2. This one's the area of the sector formula, and this is the area of a triangle who the outside edge is the height, which is, that's why it's using tangent. So it's opposite over adjacent, opposite times adjacent in this case. And then multiply them all by 2, do the reciprocal trick, and once again, and then you come out to finding that the answer ends up being 1. Now, this also works. So the limit as x approaches 0, as the angle approaches 0, as that angle, because you can't find the area of something at 0, of course, but as it's approaching a height of 0, then it's always going to equal an answer of 1. And it does not actually matter. It could be sine of x over x. It could be sine of 4x over 4x. It could be sine of 2x over 2x. As long as the argument is the same as the denominator, this will always be true. And you do not have to, on AP exam, prove this. This is not something you have to memorize. It's not something you need to know in detail. You just need to understand that this answer is 1. And it kind of does help to understand this whole reason why algebraically that it does. And like I said, I do apologize for not having the 15 minutes that is required to really go through this more in depth. So that is really the squeeze theorem. So squeeze theorem proves, it's not really, this is one of the more common uses of the squeeze theorem to prove that the limit as x approaches 0 of sine of any argument over itself will always equal 1. It's really just a shortcut in the end. It's something we're going to use to make life a little bit easier. All right, so we look at this first example here, and we got some trig involved. So tangent of x is sine over cosine. You should know that by now with pretty much with ease. And then I use leave change, leave the top alone over complex fraction, change the multiply, change it to the reciprocal. Now from here, then I can split this up into, I'm going to multiply it. So sine of x times 1 is sine of x, and then this becomes x times cosine of x. Actually, no, I'm going to split it. Sorry, I'm going a little too fast here. So you're going to split this up using your properties into a limit as x approaches 0 of this times the limit as x approaches 0 of the other term. So we've really just split it up into two different terms. And now we can basically solve each one separately. Now, the reason why we do this, and I guess I really shouldn't have passed that, is because this is an indeterminate solution. If I plug 0 in for x here, and I plug 0 in for x here, you're going to get 0, 0. That is 0. That is also 0. And that's not a real solution. This is a way of eliminating the indeterminate. So it's kind of like what we did before when we were trying to erase the holes. So this is our way of erasing the hole. If I put 0 here and 0 here, yeah, that's going to be 0 over 0. But we've already proven using the squeeze theorem that this answer is 1. And that's what I was telling you about. This is basically the little shortcut here. Now I can plug 0 in over here and get 1 over cosine of 0. And cosine of 0, you should know by now, is 1. So 1 divided by 1 is 1. And boom, there's your answer. It's just a nice little shortcut. All right, this question is very similar. The only difference here is we're going to use the conjugate. So we're going to use the conjugate of this like we've used in a prior video. This times this gives us this. Now you should know on your most basic trig identity, 1 over cosine squared is equal to sine squared. So that's how I got to the sine squared. And then I split it up into two pieces, kind of like I did on the last problem. So I can use my properties to split it up into two limit notations. Then I can solve each one of these separately. Once again, we know this is 1 because of the squeeze theorem, proved it already. And then I can plug 0 in over here and just get my answer of 0 over 2. Obviously, anything times 0 is 0. So as we move on to example number 5. So this one's going to be a little bit different. So this time I'm going to use my properties first. And I know this is kind of like the trig identities. You really don't know exactly where to go. Just after you've done enough of these questions, you just kind of get a feel of what's expected of you. So I'm going to use my properties to split this up into two. Of course, they both have to be over x because it had to have a common denominator if you're going to split it. And this, we have limit as x approaches 0, so x obviously cancels out because anything divided by itself is 1. And therefore, the answer is just 2. Because if you put 0 in for x, well, there is no x. So obviously, the answer is just 2. And over here, we use the squeeze theorem. We already know this answer is 1. 2 minus 1 is 1. There's our answer, and we're done. So my notes up here, basically, that was my reasoning why I was able to use those properties. So I was able to split it up. So they're basically the exact same thing. This, I'm just proving that whenever you have one thing on the bottom, that basically it's the same thing as splitting it up with the same denominator. All right, so for the next question, once again, looks like we're going to use no, we're not going to use our properties. Okay, so this is actually a different trick on this question. The problem here is we cannot use the squeeze theorem. And the reason why we can't is because the argument of the trig function does not match the denominator. So my goal is to make, if this says 4x, I need to make this say 4x. And the only way to do that is to multiply the top and bottom both by 4. Now, the problem here is I can't just say this is the answer of 1 because it's not. Because that 4 right there makes it different. So I need to pull that out using my properties of limits. Once again, that's why we learned those properties. Make life easier on us and find these little shortcuts. So once I pull that 4 out, which I can do using that constant multiple rule, then I'm going to pull it out to here, and then I have, using the squeeze theorem, I have what I wanted. The answer to this is 1, as we've already proven. Once again, on the AP exam, you're not going to actually have to prove the squeeze theorem. You can just know that this answer is 1. So obviously 4 times 1 is 4. All right, so next question. Example number 7, I think this is my last one. Very similar way of doing it. I know it looks like the answer is obviously just 3 over 5, but you can't do that. Yes, that is going to obviously, no matter what this number and this number was, that was going to be what the answer is going to be. But you need to, on the AP exam, be able to prove why it is what it is, because you will be given credit basically for your work. It's not just, it could be just one answer for the, 1 point for the answer and then multiple points for actually showing the steps. Now, why does this work? For the exact same reason I did in the last one. If the argument is 3x, I want the denominator to be 3x. So I'm doing the exact same trick I did on example number 6. But then I'm going to use the same trick again to pull the 3x out and make it as the coefficient. And I'm going to do the exact same process on the bottom. I'm going to multiply both of these by 5x to make the denominator 5x. Once I've done that, I now know this is 1. I now know this is 1. 3 times 1 is 3. 5 times 1 is 5. And there's my answer. Now, I could have also, which I guess I didn't put here, is once you get down to this step, you can really just cross out the x's. I could have crossed out the x's here at this point, to be honest. Or I could just simplify, plug it in. Either way you do it, you're going to get an answer of 3/5. And that concludes the video. Thanks again for watching. Let me know if you have any questions, and I'll see you on the next video.